Hi chemistry kids, so we're going to just look at some combustion. There's a random nut here, I don't know where that's come from. So we're going to just look at combustion. So way back, unit 3, when we were looking at options for energy production, obtaining energy from fuels. I'm going to make one quick, I always say the quick one over that quick, one which is this thermochemical equations and some of our gas law bits here. So kind of these two, or maybe that one too. And then I'm going to make another one which is this mass, volume, stoic. I think some of the others are pretty, we did that again, that should be all right. Yeah, let me know if there's any of these you think we definitely have to cover. So that's what we're doing. So remember, this is your study guide, so this is giving you an outline of everything you need to know. So if you think there's something in here you have no idea what it means, let me know and we'll go back over it. So what we're looking at today, quite so big, is we're going to just revise some of the gases, and we're going to use the information from the data book to give us that background to help us out. So gases, they take up the volume of whatever container you put in. They're these little molecules kind of bouncing around. The volume can be changed. You can make them bigger and smaller. They're going to move around more with higher temperatures, and that's the gas. We get a lot of them with combustion, so this very often will be linked with our combustion questions, because we combust something, we get some oxygen and some carbon dioxide. How much of that do we get? And then we can use those as well to work out, how much energy we get, how much greenhouse gases are being given off, blah, 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 blah. Right, so the first one that we need to think about is this universal gas equation. So it's sat there nice and just like, oh look, here's some letters. Thanks for that, data book. I mean, we should be quite thankful. So what does this all mean? So remember, you have to go in and have a look at what's his face, the annotated data book online. Have a look at him. He's done it like nice and prettily. He hasn't got too much information. He's kind of cut out some of the waffle that I might add. So we'll start with this side, and P is our pressure. This is measured in kilopascals. And then we have our volume, which is in litres. Then we have N, which is number 4 moles. Oh, that should be moles. In moles. And that's mole, that's our unit. Then we have O, which is our universal gas constant. Don't need to think too much about that, how they've worked it out. It's one of those experimental things you're just given. And then the last one is temperature, which is in Kelvin. So if we are given, not Kelvin, so if we're given degrees centigrade, you need to add 273, she says. 273. So they're given to you, but it's one of those things I think most people are going to remember. 273. So to convert from that to that, that's what you're doing. So this is the kind of question you'll be given, work out the volume, or work out the pressure, or work out blah, 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 using these forms, and they've given it to you on page. So it's set up here, looking nice and innocent with all those factors in here. So that's under non-standard lab conditions. But we also will have some questions where they're looking at standard lab conditions. So standard lab conditions are when we're looking at these ideal gases, so we're assuming all of our gases are ideal gases. Ideal gases means they don't react with anything else when they're in a gas, or they're not behaving in a kind of strange, non-standard way. They're not going to ask you anything about non-ideal gases because it's beyond the scope. You know, why would they add that kind of weirdness in here? But if we have our ideal gas, which is all of our gases as long as you are concerned, the molar volume of it, so a mole of our thing at standard lab conditions, so 25 degrees and 100 kPa, is going to be 24.8 litres. So I have 1 mole of oxygen at 25 degrees C and 100 kPa. That's how many litres it's going to take up. Same for nitrogen or neon or gaseous carbon. I don't know how hot that would be. Oh, that couldn't be there. Anyway, so that's, you know, at 25 degrees C. So what we need to think about, though, is the different units they're going to give you. So SLC is 25 degrees centigrade and woman fiddling with a data book is such fun. And 100 kPa. They might give it to you then kPa, or to be tricksy, and who knows what they're gonna do. Their 100 kPa is equal to 750 millimeters of mercury, or 0.987 atmos. They might give you an atmos figure, and if you think, oh, it's like 1 is the same, no, yeah, you have to make sure that you are checking that this value here, or this value here, is equal to that. So that's kind of your first stumbling block. If you see that one or that one being given, that you have to double check that it's that and it's fitting in standard lab conditions or not. So if it's not, then you go and use this. If it is standard lab conditions, use volume equals volume, molar volume. So volume over molar volume gives us our number of moles. So for anything not fitting our standard lab conditions, we're going to use this, but experiments can be done under standard lab conditions, and we can get this equation here, which is that 1 mole of anything is going to give us this volume, which is our kind of constant. SLC. So if I know I've got 10 litres, I can divide it by this and it gives me the number of moles. So I can rearrange that equation to give that. And then that's much easier than using all this and having to slot all those numbers in. So just check what the question's doing. Give yourself not a lot of time, but make sure you just stop when you get these questions and double check what kind of equation you can be using. This is good. If you slot these numbers in and do this one, when you only need to do this one, it should work. It shouldn't take away the marks for you, but I would, this is much easier. So just take the time. I would look at some questions and see, I'll give you some questions, see what kind of things they're asking before you start panicking about these too much. And remember, if you stuff up, you still get some marks as long as you're doing something. Well, it depends what you're doing, but as long as there's something on the page they're trying to give you a mark, not take it away. So I found this question that I think is a good one because it's not a VC, it's not a previous exam question, but I'm leaving those for you kind of at this point because I think the feedback you get is pretty good. So we have this question. Right. So first part. Give myself new space. There you go. Right, propane gas, and my highlighters have run away. There you go. propane gas, propane. So step 1, propane. Propane. Whoever's in with you lot is going to be very annoyed at all the paper ruffling. Right. Propane. Too easy. H gas. Yeah. Was combusted in the presence of abundant oxygen at 1 atmosphere and 25 degrees C with 0.1 litres of propane reacting. Right. Write a balanced thermochemical equation for the combustion of propane. So the more, when it's saying thermochemical equation, it means we need to have this included. So they need to know this information as well. They need to know this. Remember, because it's giving off heat, this is a negative. This is our delta H, and it's negative. So make sure you pop in that negative sign in. So whatever it is, we can pop that bit in here. Oh, delta H equals negative. There you go. And I'm going to suggest that probably is your 1 mark. Just having that to check in so you know it's the thermochemical equation. So remember, we have to have our units. There's a bit at the top of the exam, you know, where it says you've got to include all your units, your states. So we'll start with, no, we start with writing the wrong thing. Plus, so it says there's abundant oxygen, so that means we're getting water and carbon dioxide. That was a nice thing to give us. That's gas. That's gas. That's a gas. No, that's a gas. That's a liquid. It's 25. So this is a 25, so that's going to be a liquid. Yeah, just check your temperatures before you get with that. I don't know how strict they're going to be on that. I would suggest they're going to be a bit fuzzy, but we'll see how we go. Right, so I've got my carbons first. So I've got 3 here, so try 3 here. Then that means I've got 6 oxygens. So I'm going to 3 here. Oh, except I'm forgetting that one. So let's do my hydrogens. Oh, you can tell I'm tired. 8, 4 hydrogens. That's 4, 6, 10, 5. So 2 marks. I've got my thermochemical equation, which is a bit of a mess, and then I have my value here. I calculate the volume of carbon dioxide produced by this reaction after the system returned to its original pressure, but at 48 degrees centigrade. Right. Original pressure. So original pressure is 1 atmosphere. Well, the question is wrong, because that one says 25. Right. Teacher checking what she did previously. Yeah, I don't know why it's giving me 48 there. We'll go with this 25. Might change everything else, but that's fine. That's what I worked out the first time. So what we've got is we've got atmospheres is equal to 1. So got 1 atmosphere, which is I don't know about that one. I think I didn't work out how I got that. So 1 atmosphere is 1.13. Oh. Yeah. 1 0.13 kPa. So this is not. So it's not standard lab conditions, so we have to use PV, etc. If this was 100, 0.987 atmos, then that would be 100 kPa, and we could use the V equals over VM, but it's not, but it's close enough, I think, that you might sneak in and think you're doing something else. Right, our volume, they give us up here is 0.1 liters. Our temperature is the one that they messed up. 25 degrees C, which is equal to 25 plus 273. Right, so we can use PV equals nRT, but we need to rearrange it because what we're trying to do is find our volume. Of carbon dioxide, not our volume of oxygen, which is what we have here. Right, you will all have your own kind of ways of laying things out because of maths and whatever. Just make sure you're keeping it logical, and I would make sure you put a box around your answer if you know, like me, you're a bit of a mess and it's all going to be a bit of a way. So I need to rearrange my equation, so that's N equals. It's going to then tell me how many moles I have. This is a big question, actually. How many marks is it for? Oh, that makes sense then. It's not too crazy for 4 marks. So, then. Right, so we slot these values in. So so that's our pressure and our volume, and then our RT is, so there's our R, 8.31 times the temperature, which is 298. And I popped that in my calculator earlier. What I got was 4.09. Right, so that's how many moles of propane we have. Now what we want to do is find our volume. Oh, no, I know what I've done. Ignore me. Right, so what I have done is I've read the question, and then I've read the question right the first time, and then wrong the first time. So what it's saying, calculate the produced by the reaction after the system has returned to operational. So what I was doing this step, it's not a very well written question. What I was doing here is I'm finding, with the 25, I'm finding my original up here, and then it gets changed, the temperature then gets changed to 48. So I'm using this first to find how many moles reacted, and then I'm using this temperature here to find out the volume. This is a tricksy question, so I don't think they're going to give you anything this tricksy, so watch me struggle through it and think, I hope I don't have to do that. Right, so you started with 25. We've got this many. Then we raise the temperature to get this value here. So what we have is this many moles of propane, and we want to find our moles of CO2. I think I'm making this more confusing than it needs to be. Right, so we have 3 times as many of our carbon dioxide as we do propane. So our number of, we just have to times that by 3. No, T equals, yeah, we times that by, times our number of moles of, oh my lord, see, get proper amounts of sleep, and then you will be able to do maths questions. 4.09 times 3. Right, so that's how much of our carbon dioxide we have over here. Remember, you're not going to simplify here. You're not going to use this value for the rest of your calculations. You're going to use the value from your calculator. Don't simplify to the end because it will make everything slightly off, and that's going to mess you up a bit. So I'd suggest maybe spend some time loving your calculator, learning maybe if you can store values. I know you can't store them when you go in, but you can probably store values as you go along somehow. Depends on your calculator, I guess. Right, so this is how many moles of carbon dioxide are given off by our reaction. So we now need to slot the new values in. So we have we want to find our volume of carbon dioxide. So NRD. I would use a pencil, personally. So, because I'm a messy so-and-so. But, you know, it doesn't really come up very well. Make sure you write hard if you use a pencil, because they're scanning it, and if it doesn't come out properly, there's all kinds of hoo-ha. So, right, so number of moles is this value from here. So if you stuffed up somewhere along the line and put the wrong one in, remember that consecutive mark thing. Then we've got our 8.31, which is my constant. Then we've got temperature in Kelvin, so the temperature's gone up, so it's 48 plus 273 because they don't give us Kelvin, and then that is divided by P, pressure. So whack this into a calculator. I'm going to put brackets from that. And we get 0.324 liters. And what was 212. Right, so that's how many litres of CO2 are given off in this reaction. I think this is a bit too hard. No, I think they would break this up into 2, especially with the COVID stuff, rather than try and make you go thing. Or they would need to rewrite this question. I think this question is badly written. I think the fact I understood it and they didn't understand it means we would assume that most VCE students would struggle to understand. No, well, yeah. You lot, well, some of you are smarter than me, but I think it's just overly complicated. Right, so calculate the mass of carbon dioxide produced by this reaction. So this is our consecutive mark. So if you stuff up, if you get stuck, just put 1 or 3 or 2, no, maybe 2 rather than 3. Something that will, be easy to work with and mean that you can show you understand the rest of it. So you might even want to write a note saying, couldn't do last step errors, used 2 litres or use 0.2 litres or something to make it clear to the examiner that you understand you stuffed up or whatever. Anyway, so we have our number of CO2 equals, what did we have? 1.23 times 10 to the minus 2. Our mass of CO2 equals 1.23 times to the minus 2 times carbon is 12 plus oxygen, which is 16 plus 16. I'm going to keep with this value because that's what they used in the first bit. Right, calculate the total energy released by propane in this reaction. Again, consecutive marks. If you stuffed up the first bit, kind of flows through. So our energy equals delta H times number of. So we need to know listener value, which is in the data book, and our number of moles that are given off. So we have 0, and we times that by a number of propanes, which was 4.09 times 10 to the minus 3, which gives me if you're not sure of the units, make sure you are including your units, otherwise it's mostly useless. We should have there are units here, so you should be all good with your units. Last one is thinking about why we do this, why we care. I think they're going to slot some of these in. Explain an environmental impact of this process. So if we look at our process, we have propane being combusted, giving us water and carbon dioxide. So carbon dioxide is produced. I think that's, what is 1 mark? 2 marks, you might say something else, but I think this is 1 mark. Identifying carbon dioxide isn't the greatest thing we've ever seen. It's greenhouse gas. That's all we need. No waffling on, no nothing. Cool. Right. Have fun.